So first up, we have to find the capacitance in a series circuit. Capacitor when the capacitors are in a series. So likewise, right here, you have to find the total capacitance with a C equivalent, which is equal to Q over V. So hence it's equal to Q over V1 plus V2. So as you can see, the voltage 1, voltage 2 in the diagram. So you total them up, and since you get C equals Q over V and V equals Q over C, you can substitute those and get Q over C1 plus Q over C2. And after that, if you simplify it, you get equals to 1 over C1 plus 1 over C2. And that's why the equivalent resistor capacitor is, the equation would be, it's 1 over C total is equal to 1 over C1 plus 1 over C2, and so on, depending on how many capacitors there are. And you just flip it over at the end in order to get the total capacitance in the series. And likewise, in order to calculate the total capacitance in a parallel, you just have to add up the capacitance C1 to C2, and we can get that from the derivation again. C equals Q over V, and then Q1 plus Q2 over V. The total V, because in a parallel, the delta V doesn't change. You get Q1 over V plus Q2 over V, and exactly that, you get C1 plus C2 equals the total capacitance. And that's why in a parallel, capacitance is the way it is. So next up, we have to find how an RC circuit has been charged. So again, in an RC circuit, you can see this regular setup, and the switch is closed at time 0. So again, we say that the V terminal, which is a voltage at the battery, which is VT, is a negative VT, plus IR, again the voltage at the resistor, which is IR, because of the resistor, and then plus VC at the capacitance should be equal to 0. And again, you can make substitutions such as C equals Q over V and V equals Q over C. And then finally you get negative Vt plus IR plus Q over C is equal to 0. Next, next you can simplify that further. You get negative Vt plus IR equals 0. And since Q over C is equal to 0, that's why you can simplify that. Negative Vt plus IR equals 0, and then Vt equals IR. So negative Vt plus IR plus Vc is equal to 0, and since I is equal to 0, Vt is equal to Vc. So that's how an RC circuit and an RC charging occurs on the capacitance plate. So next up, we have to find how an RC circuit, the discharging occurs in an RC circuit. You can see there's a capacitance plate and a resistor with a switch which is closed at time t equals 0. Again, the negative voltage at the capacitance plus IR due to the resistance is equal to 0, and again I is equal to VC over R and Q is equal to C over CV. And if you make those substitutions, you get VC minus IR is equal to 0, and since the voltage of the capacitance is 0, Q is also equal to 0. So that's how discharging at a capacitance occur, which is because Q is equal to, and Q does end up equaling 0 at the end of that time frame. So here we have an RL circuit. To get started, let's see what an RL circuit consists of. It consists of a voltage EMF, which is just a battery, so that's the V voltage. There is a resistor in the middle. There can be multiple. You can have to calculate the total resistance. And finally, you have an inductor, which is denoted with an L, and which usually we calculate through using L times di over dt. We'll learn about that more in the next few slides. So let's see what an RL circuit is. So when an RL circuit is first turned on, the inductor opposes the current flow and acts like an open circuit. So when the circuit is when the switch has been closed, the inductor opposes the current flow. So the current is flowing from V to R to L, and this L is gonna oppose the current flow and act as an open circuit. But however, after some time, the inductor keeps the current going and acts almost like a short. So the inductor is always going to try to keep the current flowing and everything, and try to oppose any change. But after a long time, when the battery is removed, when the V is gone, the inductor acts like a V. So basically, an inductor gets charged with all that current, and then acts like that V to keep the current going. Remember, the inductor's job is to oppose any change and keep everything going. Next, And as the resistor dissipates power, the current will decay exponentially to zero. So its graph's going to go downwards, and it's going to be like a curve, slowly slowly approaching zero, but never going to touch zero. So that's going to happen as the resistor dissipates power. The current's going to go down to zero. So again, an RL circuit consists of a battery, a resistor, and an inductor. And again, when and the inductor is again charged, through that current flowing through the resistor, and acts like a voltage towards that. Alright, so first we have to find the current in RL circuits. So first what we set up is our integral on the closed interval of E dot dl, which is equal to delta phi b over dt. So d phi b dt, which is just a change in the magnetic flux or a change in time, is equal to minus L di dt, which is di dt is the change in the rate of change of the current, and L is the okay, skip that. And then so if you look at the circuit starts, and there's already an automatic voltage of IR over here due to the resistor, and the current's moving to the right from the beginning, so it's going that way. So IR is already there, and the V is going to oppose in the other direction. That's why it's IR minus V is equal to a minus L di dt, because that's where electric field is zero. And after that, when you simplify, you get this, and then do the separation of variables. You set it up into these integrals. So you integrate the left side from I equals 0 to I, because you have di over here, and the left side equals t equals 0 to t, because it's a dt, the di dt. You integrate, and you get natural log of I minus v over r from 0 to I, remember, and then is equal to negative r over lt, because those are the integration answers to that question. And after more simplification, you just end up getting natural log of I minus v over r minus natural log of negative v over r is equal to negative RLT. And you keep simplifying that further, you get natural log of I minus v over r over negative v over r is equal to negative r over L times t. And moving on from that, it's I minus v over r minus over negative v over r is equal to e to the negative RLT. So you just raise both sides to the e in order to solve for Ri. After you've raised all of that, you get to simplification. I minus VR is equal to negative V over R, e to the negative R over LT, and you finally simplify it to I equals V over R times 1 minus e to the negative R over LT. So this is the formula to find the current in RL circuits. Where V is the voltage of the battery over the resistance, total resistance R, times 1 minus e to the negative R over L, and L is again the inductor, and that's what it was in the beginning. L is the inductor. Alright, so next up we have to find the voltage in an RL circuit. So first of all, we set up the formula, the voltage, the function voltage over a period of time is equal to L di dt, again the change in the current, and L is again the inductor, which is equal to this, and di. So essentially we only need to find the derivative of I, because with respect to time, because that's what and we already know I from our previous example. So I again is v over r times 1 minus e to the negative r over lt. So that's I. You plug that into the I into the I over here, and you differentiate it as with respect to time. So with that, after differentiating, you can pull out the constant v over r. So that gets pulled out in the next step. So L times v over r, the derivative with respect to time of 1 minus e to the negative r over lt. And again, you further simplify that. You go next step is equal to L times v over r times negative e to the negative r over L times t times negative r to the L. Remember, this is again differentiating, and this is using chain rule, so you cannot forget the times the negative R over L again. And again, and then you just simplify it further. You get the voltage is equal to voltage times e to the negative R over LT, and for our purposes, tau is equal to L over R. So you can again replace negative R over L with tau, with 1 over tau, which and in the second part you can just say that voltage in an RL circuit is also equal to voltage times e to the negative t over tau. So these two are fundamental equations in order to find the voltage, where V is the voltage of the battery in the beginning, R again is the resistance, and L again is the inductor. Same thing, same concept. Next up, we have to find the rate of change of current in RL circuits. We have already done this before with the voltage, but we can do this again. It's simply just di dt, di over dt, and we have to differentiate our I with respect to time. Again, the same thing, V over R times 1 minus e to the negative R over L times t, and you differentiate it with respect to time. So you pull out the constants V over R. Again, the same process. You go down again. You get V over R times negative e to negative R over L t times again negative R over L. Because of chain rule, we must differentiate, and we must keep in mind what we're differentiating in with respect to time. And when you simplify all that, you get V over L times e to the negative R over L t. So that's what the equation is, and again you can replace negative R over L with negative 1 over tau. So V over L times e to the negative t over tau. So that's what the equation would be to find the rate of change of current in RL circuits. And here it's the V is the voltage in the beginning, R is again the resistance, L is again the inductor in the circuit. So yes, that's how you find the rate of change of current in RL circuit.